In this lecture video, I will present one example problem of an electric force calculation. I'll remind you of some of the important quantities that we deal with commonly when we're discussing electric force. Lowercase e represents the charge of a proton. K is the so-called electric force constant. And we have an angstrom equals this many meters, a very small fraction of a meter. I show two objects whose charges are Q1 and Q2 separated by a distance r. The absolute values of those charges are capital Q1, capital Q2. The equation in the box shows you what force each particle exerts on the other one, KQQ over r squared. Here's our sample problem. We have a square. At three of the vertices we have a proton, and that object is a doubly ionized magnesium ion. It was once a magnesium atom. Two electrons were snatched away from it, leaving behind an excess of two charges equivalent to two proton charges, double plus. Its charge is 2 times the charge of a proton. The length of each side of the square is 3 times 10 to the negative 10 meters, otherwise known as 3 angstroms. We wish to calculate the net force, total force, on that proton there. And we do that by recognizing that there are two pushes on that charge. There's a push by that proton, acts that way, call that force A. And then there's a force exerted on that proton by that double the ionized magnesium ion, and it points along the diagonal direction like this. Let's call that force B. Before we determine the net force on that charge, let's find the magnitudes, the lengths of these two vectors A and B. Well, the A vector is K times 2E times E divided by r squared. This looks like K times 2E squared. R squared is the square of the hypotenuse of this right triangle. So it's equal to the sum of the squares of these two sides. This is 9 times 10 to the negative 20 squared, and this is also the same, 9 times 10 to the negative 20. And so the total value, r squared, is 18 times 10 to the negative 20. When one substitutes in the values of K here and E there, this is what you get after you convert the answer into nanonewtons. A nanonewton is a billionth of a newton, 10 to the negative 9 of a newton. Well, that takes care of the magnitude or length of the A vector. Now let's find the length of the B vector. B equals K times E times E over that distance squared, which is A, which is 9 times 10 to the negative 20. When one substitutes in for the values of K and E, you get 2.56 nanonewtons. This is a typo here. This should be 2.56. Numbers are the same, coincidentally. Let's not make a big deal out of the fact that the numbers are the same. No meaning whatsoever. Excuse me. Now what we do is the following. We recognize that the total vector, the sum vector, is the sum of the separate vectors A and B. The magnitude of the S vector, its length, is found this way. It's a square root of the sum of the squares of the S components. S sub x is A sub x plus B sub x, and this works out to the full value of A, which is 2.56 plus B sub x. Well, B sub x is the length of B times the cosine of this angle. That angle is 45 degrees. And so this is plus 2.56 cosine of 45 degrees. Now I'll calculate what that is. (2.56) plus 2.56 cos 45, and we're left with the answer 4.37. Nanonewtons. S sub y is equal to A sub y plus B sub y, but A sub y is 0, and B sub y is 2.56 times the sine of 45 degrees. That is equal to 2.56 cos 45, 1.81. And the units are nanonewtons. Final result for S, it's the square root of 4.37 plus 1.81 squared, square root of that sum. Final answer is coming. 4.37 square it plus 1.81 square it, add it, sum of them square rooted. Final result, at long last, 4.73 nanonewtons.